In this video, we're going to talk about what it means for a subset of a metric space to be compact. So the concept of compactness is related to the concept of closed and bounded. In the real number line, a closed and bounded interval, like the closed interval from 0 to 1, has certain properties, like if you have a continuous function defined on the interval, it attains a maximum and minimum. That's one of the properties of closed intervals in the real line. But it turns out that when you analyze the proof of how that works, and when you think about what are the things that make closed intervals work the way they work, it's actually not so much that they are closed and bounded, but that they have a certain property called compactness. And it's that property of compactness that we're going to define in this video. So to do that, I have to give some other definitions first. The first definition is the concept of an open cover. So here's a definition. An open cover of a set S in a metric space E is a collection, say a set of sets U alpha over some indexing set I of open subsets of E such that S is contained in the union of the U alphas. So this I is the indexing set, because if you have a collection of sets, it's indexed by some set. And the indexing set is what I call I. The indexing set doesn't have to be countable. So for instance, your sets U sub alpha, the collection of U sub alpha, might not be countable. So you might not be able to call the sets U1, U2, U3, etc. Okay. If your indexing set I were a countable set, then you could enumerate your sets U sub alpha as U sub 1, U sub 2, U sub 3, etc. But in general, you can't. So this is just any collection of open subsets of E, possibly countable, possibly uncountable, such that S is contained in the union of the U alphas. So here's an example. Take any metric space and S, so let S be any subset of any metric space. Then for each P in S, the set, which is the open set of radius 1 centered at P, contains P, right? Oh, it contains the set consisting of P. So that means that S is contained in the union over all P and S of the ball of radius 1 centered at P. Of course, the 1 wasn't that important. You can just take any open ball centered at P. And if you take the union, then S is contained in that union. So let's say that S was the real number line. Then you're just taking at each real number, you're just taking an interval of radius 1, right, at each point, and that union is going to contain the entire real number line. Excuse me. In that case, the union is just going to equal the real number line. Okay. And notice that since, here you're taking the open ball in E. So the union might not be contained in S. So you don't necessarily have the reverse inclusion. So for instance, let's say that S was just this interval, this closed interval, right? And then you just do the same thing. So at each point in S, you take a ball of radius 1 centered at the point, and then you take the union. Well, in that case, the union, because of the corners, because of the edges of the interval, when you take a ball of radius 1 centered at that endpoint, then you're going to get points that are outside S. So in general, S is just a subset of the union. It's not necessarily equal to the union. Okay, here's another example. Suppose that S is a subset of a metric space E. Take U to be E. Well, then S is a subset of U. So the set consisting of U is an open cover of S. So in the previous example, S is contained in the union of these open balls, so the collection of open balls of radius 1, and this is indexed by P and S, is an open cover of S. So in this next example, the set consisting of U is an open cover of S. Now, notice that an open cover is a set, but the elements of the set are themselves open sets. So in this second example, okay, this open cover, this is a set consisting of the set U, right? So how many, this open cover has one element in it, U. So this is a open cover of S. This is a finite cover. Okay, this is a finite cover. Now U itself may be infinite, an infinite set, but the cover itself is finite. Do we understand the distinction? Because this open cover, okay, this set has only one element in it. So if you have a one element set, that's a finite set, right? That's an important thing to keep in mind when you are thinking about the definition of a cover. So now let's turn to the definition of a subcover of a cover. So again, suppose that S is a subset of a metric space E, and that you have an open cover of S. A subcover of this cover is a subset of this cover that is also an open cover of S. Well, okay, if you have an open cover of S, then any subcover is going to be open. So it's really saying that the subcover, that the subset is a cover, right? That the subset covers S. That's the real heart of the definition. So a subcover is a subset of the cover that also covers S. Okay? So, for example, here's a trivial example. You could just take the subcover to be the actual cover, because a set is a subset of itself, right? This subcover, in the definition, it says a subset. It doesn't have to be a proper subset. So every open cover of S is a subcover of S. Every open cover of S is a subcover oh, I should be more precise. It's a subcover of that open cover. Every open cover of S is a subcover of itself. Here's a less trivial example. Suppose that S is the closed interval from 0 to 1. That's a subset of R, right? So here's the interval from 0 to 1. So this is your set S, and then my underlying metric space E is R. Then the set, which consists of all open balls of radius 2/3 centered at X is an S, is an open cover of S. Right? So this open cover is just at every point you take a ball of radius 2/3 centered at that point, and you just do it for every single point in your interval, and that is an open cover. And I can take a subcover by looking at the set, which is the ball of radius 2/3 centered at 0, and the ball of radius 2/3 centered at 1. Because if I take 0 and I take the ball of radius 2/3, and then I take 1, and then I also take the ball of radius 2/3 centered at 1, then the union of those two open intervals contains the interval from 0 to 1. So this set is an open subcover, or just a subcover, of my original cover. So my original cover ranged over all X and S. Now here I just have a 2-element subset. So this is a subcover, because it's a subset, and my set S is contained in the union of the sets in this subset. Oops. Like that. Okay, so thing to keep in mind is that an open cover is a set whose elements are themselves open sets. So a subcover of this open cover is a set whose elements are among those open sets of E. We are not taking subsets of the open sets. So here's an example. So if, again, you look at S, which is the closed interval from 0 to 1, okay, if I take the set, which is the ball of radius 1/2 centered at 0, the ball of radius 1/2 centered at 1/2, the ball of radius 1/2 centered at 1, okay, this is an open cover of S. But it is not a subcover of the cover that I was looking at before. It's not a subcover of the cover consisting of all balls of radius 2/3. because these are not even, see, if you look at this, the ball of radius a half, okay, that is, this ball is not, these balls are not balls in my cover, right? I have the intervals in my cover have radius 2/3, and taking an open subcover means that you're picking some of these intervals of radius 2/3. So if you have interval of radius half, that's not even in your cover. Okay, so what we're not doing when we're talking about subcovers is we aren't saying, okay, here's one of my open intervals. It has radius 2/3 centered at 0, and you're taking like a subset of it. That's not what you're doing when you're taking a subcover. Okay, you're taking, it might help to use the word collection instead of set. So an open cover is a collection of open sets, right? And a subcover is a subcollection of that collection of open sets. You're picking certain of those open sets, but you're not taking like parts of the individual open sets to have a subcover. Okay, that's very important to keep in mind. That's one of the tricky things about this definition. Okay, so now we have defined open cover and a subcover. Now we are ready to define compactness. So a subset, now it's often typical to use K, but you could use whatever letter you want. So a subset K of a metric space E is called compact if for every open cover U alpha of K, this open cover has a finite subcover. So there are finitely many indices alpha 1 through alpha k such that, or alpha n, let's say, such that k is contained in the union of the U alpha 1 to U alpha n. Or another way of phrasing it that you sometimes see is there is a finite subset J in I such that K is contained in the union of U alpha where alpha is in J. That's one way to say the same thing except without having to use all these subscripts. Okay, and more succinctly, the subset K is compact if every open cover of K has a finite subcover. Okay. Now the for every is important here. Every open cover has a finite subcover. So if you have a set, okay, if you just take the, so you have S as a subset of E. If you take, where was the example I had? Yeah, this example, S is a subset of E. If you take U to be E, that's a finite cover. So it has a finite subcover. You just take the set consisting of U, right? That's a, or E in this case. That's a example of a cover with a finite subcover. But to be compact means that no matter what cover you start with, It could be a weird cover. That cover must have a finite subcover. Okay, so all the possible open covers of your set have a finite subcover. So that's what it means for a subset to be compact. And in later videos, we're going to look at some examples and some properties of this. But this video is just about the definition.